Action.
Okay. What we're going to look at now is measuring an actual AC type signal with the oscilloscope. So far what we've done is we've taken a look at how a battery registers on an oscilloscope display, and that's pretty simple. You just see the line go up or down depending on the polarity of the battery. Now I want to take a look at an actual waveform, and then I want to show you something that's another feature you find in most oscilloscopes, and that is we have a test point right here built in. It says calibration 2 volts peak to peak 1 kilohertz. Most oscilloscopes have this built in. It's a built-in square wave signal generator right into the face of the scope. All I have to do is take my test probe, hook it to that point right there, and I have myself a waveform. If I turn up the sensitivity, now I can see the shape of that waveform, and it's clearly a square wave. I can also now play around with my time division control, my time base, and see what effect that has on the appearance of the waveform. I'm looking at the same wave, but by moving this knob, I'm not actually changing the signal. I'm simply changing its appearance. And the way I like to relate this, especially to someone with a mechanical background, is I like to relate it to something called a stroboscope. If you're taking a look, if you ever used a timing light on a car, for example, to time a car's ignition, it's a special xenon bulb that hooks up to one of these spark plug wires, and as you point the xenon bulb at the rotating vibration dampener, they've got a readout that shows you the timing of the engine, how far before or after top dead center the number 1 cylinder is firing. This strobe light flashes once every firing cycle of number 1 cylinder, and so what happens is you get this, it's like a strobe light effect. It tends to freeze the rotating motion because your eyes only see this vibration dampener every time the light flashes. You see it once every other rotation in the same spot, and so you can see where that marker is. By the same token, we have a waveform that's going up and down continuously. What we want to do is make that appear frozen on the screen. So what we do, or what the oscilloscope does, is it takes the dot that we saw earlier that was drifting across the screen very slowly. Right there, we're taking this dot and we're speeding it up, and furthermore what we're doing is we're synchronizing that dot to the leading edge of our waveform so that when we attach it, it makes it look like the waveform is standing still. Even though the waveform is actually going up and down, it's like a strobe light that has caught the motion of that wave. If we make the sweep go faster, what we see here is fewer cycles of the waveform. And I can move the position left and right, and I can see exactly where my waveform begins. We happen to have the triggering set so that it starts the sweep across the screen on the rising edge, which is why we don't actually see that rising edge. See just a tiny bit of it right there. It's a very thin edge. Then we see the full top of the wave, falling edge, full bottom of the wave, rising edge, full top, falling edge, full bottom. There's a few things we can tell about this waveform. We notice that it starts at 0 volts and goes up from 0. For example, if I disconnect this, you can see right now with 0 volts, I show the line straight across the screen in the middle, right where I've got it set for my neutral position. As I connect it, I see the voltage causing it to rise but never fall below 0. So it's really a pulsating DC waveform. Now there may be times that I want this oscilloscope to automatically center the wave. In other words, let's say I have a waveform that's going up and down, but that entire waveform is elevated or biased with the DC voltage. There may be times I want to get rid of that elevation and just show the waveform itself, that the oscillating part centered around the screen. And if I want to do that, the way I do so is I use this control down here. This is called my coupling control. Currently it's set on DC coupling, which is the same thing as an amplifier circuit that has DC coupling between stages. DC signals pass through unhindered. If I move it to AC coupling, what that does is it connects the input in series with the capacitor. So now only the alternating part of the waveform gets through. The DC bias is taken away. I want to show you something, how this works. If I take a look at DC, in fact, let's go ahead and do this. There's a little trick I can pull. I can connect this to the positive side of the battery, and I can connect the negative side of the battery to my square wave. What I've done now is I have added 9 volts DC to that 2 volt peak to peak square wave. It's just a simple trick. And so I've taken that 2 volt peak to peak square wave now and lifted it 9 volts above 0. Well, I can see right now it's a fairly small wave. It's not even tall enough for the oscilloscope to lock into it, so I'm having trouble even seeing it as a wave. Of course, I could turn my sensitivity up so that wave looks taller, but if I do that, what happens? It blows right off the screen. Now it's completely off the screen because 9 volts is above these marks. Well, here's a trick I can do. I can set this to AC coupling right here. In AC coupling, it connects a capacitor in series with the input, which means it will filter out or screen out this 9 volt DC bias so that all I see now is the square wave. And as I turn the sensitivity up or down, the wave remains centered. Even though the DC is still there and would normally be blowing the waveform clear off the screen, in this case it doesn't because I've filtered out the DC. So that's a very, very, very handy tool right there, the AC coupling. Now, my general recommendation is this. You try to keep this on DC coupling unless you have to go to AC. And the reason why is this, because with low frequency waveforms, that capacitor that is placed in series with the input can actually cause an RC time constant distortion of the wave. So if you're looking at a fairly slow waveform, maybe a 40, 50, or 60 hertz square wave, that square wave will start to look rounded. It'll be distorted by that capacitor. So this is really only useful at higher frequencies. But it still is useful. But if you can get away with not using that and just using DC coupling, you're guaranteed to get a pure view of the shape of that wave. So we're going to take another look at this and understand more about the square wave. I'll hook it back up. There we go. I'll turn the sensitivity up. Notice we don't have our 9 volt bias anymore, we just have the waveform. So we're able to see it without using AC coupling. Notice I didn't hook up my ground lead, which at first seems really odd because we all know voltage is measured between 2 points. But also recall that this ground lead goes to the metal chassis of the oscilloscope frame. And that's exactly where the other terminal of my built-in square wave source goes. It's already built in to have its other terminal reference to chassis ground. So this now becomes superfluous. I don't need to do anything with it. I don't have to connect it. And that's why it works. Okay, so here we are looking at the waveform. At this point, we've already seen how the vertical sensitivity works, how we read volts vertically. I wanted to see how we actually measure time horizontally. So let's take a look at this right here. I have my time division, and presently I'm at 0.2 milliseconds per division. So I'd like to use this to determine the frequency of my waveform. So what I want to do is I want to count how long does one cycle of my waveform take. I want to see the period of that wave. So to help me out, what I'm going to do is take this position knob right here, I'm going to move it off to the side, so I've lined up the rising edge of that square wave right with one of those lines on the screen, the major divisions. And I'm going to count over. 1, 2, 3, 4, 5. So one complete cycle of the square wave takes 5 divisions. Then I get up my calculator. I'm going to take the number of divisions, 5, and I will multiply that by how many milliseconds I have per division. So times 2e to the minus 3 equals. And what I have right there is 0.2, made a mistake there. 5 divisions, this only happens when you're filming, times 0.2 e to the minus 3. There we go. 0.2 milliseconds times per division times 5 divisions gives me 1 millisecond for my entire period. So one whole cycle, the waveform takes 1/1000th of a second. Well, if that's how many seconds per cycle, and I want to know hertz, or frequency, which is cycles per second, all I have to do is invert that number, hit the 1/x button. There we go, and I have 1000. So I have a 1000 hertz waveform, 1000 cycles per second. That's exactly what it tells us down here. It says we have a 1 kilohertz waveform. This is also important because not only is this tab here useful for demonstrating some basic features of the scope, it's also useful for calibrating it. This is a built-in self-check. You can connect the probe to that terminal, and you can check and make sure this is reading accurately for volts. You can check and make sure that's reading accurately for time. So if I did not get 1 millisecond per cycle reading on my screen, I would have good reason to believe that my calibration may be off. In fact, I'll even prove that. I will take this sweep variable knob right here and move it off of calibration. And notice what happens. Now I can move it to any arbitrary point I want. If I were to try to calculate the time here, I would say, oh, one cycle takes 1, 2, 3, about 3.5 divisions. I'd try to work that out with my math, and I would falsely come to a higher frequency than 1000 hertz until I realize, oh no, this is actually off the calibrated position. I have to move it back, click, and now it's accurate. So this is a self-check. So if you hook this up to a scope, hook the scope up to its own signal, I should say, and things don't work out right, either you have a calibration issue here, or maybe the signal generator internally has a calibration issue, but one of them's off, and the scope needs servicing, or you need to very carefully check and make sure you didn't do something like that. But once again, we'll take a look at the vertical and verify we're reading properly in vertical. We've seen how that works with the 9-volt battery. Now I want to check our square wave source. So currently we are on 1 volt per division. And looking vertically, here's my center line. I'm going to go 1 division, 2 divisions. So it looks like I have 2 divisions. Each one of those is worth 1 volt. So sure enough, this is a 2 volt peak-to-peak waveform. From one peak to the other peak is 2 full volts. All right?
Yes.